Okay, silly people, here's the situation. We're taking a look at the rolling without slipping constraints, um, the constraint equations from the book, and checking if they're holonomic or not, using this law here, um, which just states if you can find an f, an integration function, such that uh, you can actually like solve for it, then it's holonomic, and if not, then it's not holonomic. What are those G's? So they are um, what are the G's? So both of these constraint equations are of the form um, Gi um, times, or no, it's Gi is a function of any of the variables in the problem. So it can be of x, it can be of y, or theta, or phi, um, times the differential of said quantity, so dxi is equal to 0, sum over I. Right? In the case of the first uh, holonomic, or in the case of the first constraint, is 0. Um, you can see that gx is just 1. It's 1 multiplied by the differential. G phi is equal to minus a sine theta. And then whenever you're doing stuff like this, you have to include the g's in terms of each of the variables within the problem. So there's also a g theta. It just happens to be 0 in this case. And there's also gy, which also happens to be 0. Uh, so the zeros there are going to cause some issues. So let's get into it. Let's look in particular at what if we have del f gx d theta, which, if it's holonomic, will be equal to del f g theta del x. Now, gx is 1, so the left-hand side should be del f del theta, but g theta is 0, so the right-hand side is 0. So this predicts that del f del theta is equal to 0, so the integrating factor should not depend on theta. Okay? Now, let's look at a different one. Let's, for instance, look at del f g phi with respect to theta equal to del f g theta del phi. Okay? G phi is minus a sine theta, so using the power rule, or not using the power rule, using the product rule, you're going to have minus a sine theta times del f del theta um, minus a cosine theta on the left-hand side times f. On the right-hand side, g theta is still 0, so the right-hand side is 0. Now look at this. The a's will cancel out. I'll move stuff to the other side, so that's just d f d theta on this side. You're doing minus cosine theta over sine theta times f. So, and the first thing that we did was look and see that the integrating factor should not be a function of theta. But then when we did the second one, we found that it will be a function of theta, which means we have a contradiction. So because of the contradiction, we can say for certain that this is not a holonomic constraint. Let's do the next one, which was dy minus or plus a cosine theta d phi is equal to 0. Okay. And it's going to be pretty much the same for this one. Gy here is 1. G phi is a cosine theta. Again, g theta is equal to 0, and so is jx. So let's first check del f gy with respect to theta, which should be equal to del fg theta with respect to y, which left-hand side should just end up being del f del theta, but the right-hand side is 0 again. So again, we're seeing from one of these relations that the function should not depend on theta. But then if you look again at f g phi with respect to theta, and then fg theta with respect to phi, you're looking at using the chain rule. So it's a cosine theta del f del theta minus f a sine theta will be equal to 0. Solving for df d theta, you have stuff which depends on theta again. So another contradiction popped up when we looked at this constraint. So dy minus a cosine theta d phi is equal to 0 is non-holonomic. That should be sine theta up there. All right.